Okay, welcome to Module 2. The topic of Module 2 is Chapter 16, nuclear energy and radioactivity. We're talking about things like radioactive dating and half-lives, all kinds of exciting stuff. Now, why is radioactivity and nuclear energy so important? Well, I look at a lot of things from the perspective of astronomy, because that's what I teach. If it weren't for nuclear energy, our sun wouldn't produce energy. The sun produces energy via nuclear energy. And without that energy, we wouldn't be around, folks. So it's a very, very important topic, and it's an often misunderstood topic, and quite often we fear things we don't understand. So part of your mission here is to understand nuclear energy, and therefore you won't worry so much about things, or at least you'll better understand things like nuclear power here on Earth, X-rays when you go to the doctor and get an X-ray. What's really going on there? Are you at greater risk of developing cancer if you fly in high-altitude aircraft a lot? If you become an airline pilot, does that increase your chances of cancer? And why is that? These are some of the topics we'll be getting into. Now remember, there is always a little explore activity right at the top of every chapter, so I encourage you to do that one. This one is about exponential growth and decay. And it tells you to get some paper clips, and it tells you to start laying those paper clips down on your book. You start out with one paper clip, and then you create little columns here. And each time you double the amount of paper clips on your column. So I have a column there that's got one paper clip, and then I created one that's got two paper clips, and so forth and so on. Next one is going to be 4 paper clips, etc., etc. You're going to see that the number of paper clips is growing exponentially. And exponential growth plays a major part when we have to in understanding radioactivity or radioactive decay. So like I said, do the activity. I'm not going to do the entire thing for you, and that'll hopefully help you understand things like half-lives, which are going to come in handy in understanding radioactive dating. How do we know how old the Earth is? We do it through radioactive dating. So all these things, and one thing I have to point out is that all this occurs, nuclear energy occurs at the level of the atom and subatomic particles. It turns out that when an atom either breaks apart or if you push several atoms together, energy is liberated in the form of, or according to Einstein's equation, E equals mc squared. I know it sounds like a lot of stuff, and it is. So pay a lot of attention when you're reading this chapter. And again, make sure you go through all your skills tests and your lab activities very carefully. Okay, so I wanted to take a little bit of time with this first slide because it's easy to just go through these really quick and not really understand what they're saying. Notice that radioactivity is defined as a process whereby unstable atomic nuclei transform and emit radiation. What the heck does that mean? What is an unstable atomic nucleus? What's an atomic nucleus? Remember, chemistry, just like any other science, really any other field of study, builds on knowledge. So we have to go back to what we learned last module. Remember, what is a nucleus? Nucleus is protons and neutrons at the center of an atom, right? So let's take a helium nucleus, for example. A helium nucleus has 2 protons in it, and it's at the center of an atom. I'm going to label the protons with a little, try to draw these fairly well. 2 little circles there with the plus signs, because we know that a proton has a positive charge, right? So there's the nucleus of my atom. Now I've left something out for the time being. Now what else do we have in an atom? Of course we have electrons, right? So I've got an electron out here, and I'll put him with a little. And again, this is not the way electrons really are. They're not little particles, but for our purposes, this is like a Bohr model. This is fine. And these electrons are zipping around. They're very, very, very low mass. They're zipping around outside of the atom. Now, why don't they just go shooting off into space and get removed from the atom entirely? Well, it's because they're attracted, right? These are negative charges, and they're attracted to the positive charges of the nucleus. And that helps you understand why electrons remain bound to the atom. But did you wonder, has this crossed your mind, why the heck does the nucleus stay together? Don't you have 2 positive charges really close to each other? If you took Physical Science 1 and you learned about Coulomb's law, you understand that two positive charges are going to repel each other. And in fact, they're going to repel each other even more when they're brought really close together. Well, in the nucleus of an atom, those protons are going to be really repelling each other. So how do they stay close to each other? Well, it turns out that there are neutrons in the nucleus. I'll just label here with an N. And neutrons are uncharged, and they provide essentially the glue, what's called the strong nuclear force, that keeps the nucleus together, keeps these two positive charges from repelling each other and ripping the nucleus apart. Now, this is a very simple atom. Helium is relatively simple. Two protons, two neutrons, that's the nucleus. That's not unstable. However, when you get to large atoms, and quite often in your the smaller elements like carbon and such, the number of protons is typically the same as the number of neutrons. But when you get really complicated atoms, really massive atoms, such as uranium, uranium has most common form of uranium, or one form of uranium is uranium-235, U-235. And it has 92 protons. That's its atomic number, which means if its mass number is 235 and its atomic number is 92, it's got 143 neutrons. Imagine what that nucleus looks like. 92 positive charges shoved in really close to each other. And it needs 143 of these glue particles to keep it all together. But even so, it is an unstable atomic nucleus. Eventually, it's going to rip apart. It just can't contain all those positive charges so close to each other. It decays, it breaks apart, and in the process, radiation is emitted. Energy is emitted. That's what this radioactive decay is all about. When you have it, particularly these really massive, it's not always uranium. There are other elements that are radioactive and other isotopes that are radioactive, but they just can't hold themselves together. They break apart, and that is the process called radioactive decay. This is a good time to dismiss maybe some misconceptions. A lot of folks, when they hear radioactivity or radiation, they assume that it is a modern thing, a byproduct of modern life, modern medical technology, such as X-rays or modern weaponry, such as the atomic bomb. Nothing could be farther from the truth. Radioactivity has always been around. Anytime you have had large elements that can spontaneously decay and give off these alpha and beta and gamma rays, we've had radioactivity. So that means that from almost day one, from the Big Bang, we had some of the very simple elements like hydrogen and helium that weren't radioactive. But then, as the first stars formed, you started to have heavier and heavier elements created. Sometimes those heavy elements could spontaneously decay, and we had radioactivity. So radioactivity is certainly nothing new, and in fact, most of the radioactivity we deal with is actually from natural sources, either in the ground. Radon is a concern for some folks who have basements, especially in certain parts of the country, because radon is a radioactive source from the ground. Another source is gamma radiation from space, just gamma rays. Now, of course, our atmosphere helps to screen out a lot of gamma radiation, but if you're a high altitude pilot flying at 30,000, 40,000 feet on a regular basis, you are more dosed with naturally occurring X-rays and gamma rays from space. Similarly for astronauts, that's one of the big concerns if we were going to do a long-term space project such as going to Mars, is how much radiation will those astronauts get dosed with. So a lot of radiation is just natural, and we just have to deal with it. It's not going away anytime soon. So it's a matter of knowing that it's there, knowing its effects, and knowing how to limit your exposure to those radiation, that type of radiation. This next series of slides deals with the products of radioactive decay. These are called particles. There are three different particles discussed in the book here. There's alpha particles, beta particles, and then gamma rays. Alpha particles are essentially a helium nucleus. So you have a radioactive element that spontaneously decays and emits an alpha particle. That means that it shoots off a helium nucleus, 2 protons, 2 neutrons. And so therefore, that's going to be a particle that's going to have a positive charge. In fact, it's got a positive 2 electric charge. And as you may have learned again, if you took Physical Science 1, a moving charge also has an electric field. I'm sorry, a magnetic field. So any particle that is moving and is charged, either positively or negatively, is going to also produce a magnetic field. And that magnetic field then will interact with a permanent magnet, such as the horseshoe magnet pictured here. And therefore, an alpha particle would be deflected in a magnetic field. In a similar way, a beta particle, which is an electron essentially, will also be deflected by a magnetic field. A gamma ray does not have a charge to it, and therefore would not be deflected by a magnetic field. And so here's a little bit more detail as far as alpha particles, beta particles, and gamma rays. And you'll be using these definitions to help you answer the next couple of questions. Okay, so armed with what you now know about alpha particles, beta particles, and gamma rays, you can now complete the skills test entitled Particle Properties. Again, I encourage you to, it's only a minute long, go ahead and watch the video real quick. That'll help you sort of work your way through the quiz, and it's pretty straightforward. Again, just keep in mind the different charges associated with the different types of particles, as well as the different masses of the different types of particles. I've already mentioned that radioactive elements such as, say, uranium-235, uranium-238 will spontaneously decay. So if you have a big old hunk of uranium, which is made up of a bunch of these atoms of uranium, do they all decay at the same time? No, not likely. It's not like they all all agree, okay, let's all decay. That's not how it works. They spontaneously decay, which means that one may not decay at the same time as another one. But it turns out that if you keep an eye on a hunk of uranium and record how long it takes before the majority of them decay, you start to come up with trends, what's called half-life. So the average amount of time that it takes for, say, half of the original uranium to turn into something else, you have what's called a half-life. So that's the amount of time that it takes for half of the uranium atoms to spontaneously decay and become some sort of daughter element. So that's what a half-life is. So if you did the explore it activity at the very beginning, remember the paper clips? You got a feel for exponential growth and exponential decay. And that's what half-life is all about. So half-life, it says that you start out with a kilogram of some sort of radioactive element. And after, in this case, in this drawing, after 1600 years, now you only have half of the amount that you started with. You started with a whole kilogram. Now you're down to a half kilogram left of undecayed substance. And in another 1600 years, you'll be left with half of that original half, or 1/4, and so forth and so on. So notice that the amount of radioactive material decreases over time, but it doesn't decrease just linearly. It doesn't just drop straight down to nothing. It's a process. Every half-life, you lose half of the amount that you previously had. So notice you start with one kilogram. After one half-life, you're down to a half kilogram. After 2 half-lives, you're down to 1/4. After 3 half-lives, you're down to 1/8, etc., etc. That is exponential decay. Now, hopefully you picked up in section 16.4 of your textbook the fact that when an element undergoes radioactive decay, it actually does change its identity. Because quite often, if it's alpha decay, if you have an alpha particle ejected, that means you lose 2 protons. You start with a certain element, but then all of a sudden that element shoots off an alpha particle. That means it loses 2 protons and 2 neutrons. And therefore, what's left has fewer protons than what it started out with. And we know that the number of protons distinguishes an element from any other element. So you have what's called transmutation, an element that changes its identity by virtue of radioactive decay. Unlike alpha decay, where you actually lose protons, in the case of beta decay, notice that there is no change in the mass number. That means the number of neutrons plus protons remains the same, and yet we know that an electron is produced in beta emission. The only way that's possible is if a neutron, remember a neutron is neutrally charged, it has no charge. If a neutron essentially decays and gives off an electron, and in the process becomes positively charged itself. So it becomes a proton. So notice that you essentially get rid of a neutron. The neutron disappears, and it shoots off an electron and becomes a proton itself. And notice that there's no change in overall charge there. You start out with a neutrally charged particle, a neutron, and you wind up producing a negatively charged particle, an electron or a beta particle, and a proton. The plus and the one single plus and one single minus both wind up they combine to be neutrally charged. So there is no change in the charge overall, nor is there a change in the mass number. What you have done is you've gotten rid of a neutron and you've added a proton to the nucleus. So therefore your atomic number actually increases by 1. So you have changed the identity of the element. Okay, so now notice that you can artificially produce elements. And in fact, that's why we've mentioned that we have 90 naturally occurring elements, but then everything else on the periodic table has been essentially created in laboratories by smashing existing elements with other particles and creating very unstable, very short-lived radioactive particles. And here your book says that everything from 93 to 115. Turns out that now there's a time of writing or time of recording this, in the year 2016, 4 more elements have been added to the most current periodic table, going up to 118, an element with atomic number of 118. It's unonosium, noctium, whatever. But notice that these are all man-made, synthetically done in labs, and again, they're very, very unstable, therefore they don't last very long. Armed now with what you know about alpha particles, beta particles, and transmutation, you should be able to take care of this transmutation of elements skills test pretty easily. Notice that there is, again, an accompanying video which will help to step you through the process. Okay, so now we get to the very interesting and important topic of radioactive radiometric dating. And probably the best known type of radiometric dating is called carbon-14 dating. And one thing that's very important to understand is that carbon-14 dating is only useful for things that have been living. And so, here's what actually happens is that while something is living, whether it's a human or a plant, let's take a plant for example, the plant is constantly doing photosynthesis, right? What's photosynthesis? It's taking it's taking carbon dioxide out of the air. It's taking water out of the ground. And then in the presence of sunlight, photosynthesis can occur. And what happens there is that the carbon dioxide and the water combine and create simple sugars called cellulose. And that cellulose is what the plant then uses to grow its stalk and its leaves, and all that stuff is made out of cellulose, these simple sugars that are made out of the water and the carbon dioxide. And of course the byproduct is oxygen. But essentially what you're doing is you're taking carbon dioxide out of the air and locking it away in the form of cellulose that makes up the plant. So you're essentially taking carbon dioxide out of the air and locking it away in the form of cellulose. Now the carbon in the carbon dioxide is usually carbon-12, but a small amount of it is carbon-14. It's an isotope of carbon. And the plant doesn't know that any different. Carbon dioxide is carbon dioxide as far as the plant cares. But carbon-14 is a radioactive isotope of carbon, and it will break down. And so once the plant dies, or a human being consumes plants and then the human being dies, you're no longer taking in fresh carbon. So once you die, all the carbon that's going to be part of that plant or that human being is locked in. And the carbon-14 then, of that carbon that's still in the plant or the human body, the carbon-14 will start breaking down. And by measuring the amount of carbon-14 daughter elements are in a sample compared to the amount of carbon-14 left, will tell you how many half-lives have occurred since that thing stopped taking in brand new carbon. And it turns out that the half-life of carbon-14 is about 5,000 years. And so therefore this is very useful in dating one's living things. And it's effective up to about 50,000 years. Because once you get beyond like 8 half-lives or so, there's so little of the radioactive material left that it's really just tough to measure. So carbon-14 dating is useful for, first of all, one's living things, and useful up to about 50,000 years into the past. Beyond that, if something is older than that, you really can't date it according to carbon-14 dating. Okay, we just described carbon-14 dating as a good way of dating things that once were living. For non-living things, you can use uranium dating. Uranium-238, uranium-235, both of those isotopes decay and create lead daughter isotopes. Both those elements have much longer half-lives than carbon-14. So not only does it allow you to date non-living things, just plain old rocks, but it also, because of their longer half-lives, allows you to get further into the past by using some of these other types of dating techniques. Okay, so you can get into the dating game yourself at this point. You know so much about radiometric dating. You can take a swing at the carbon-14 dating skills test. And this one does involve a video that you need to watch, and then you're going to answer some questions that accompany the video. The lab activity for Module 2 is Halflife. And this is a pretty cool lab activity, and again, I encourage you to watch the tutorial. The interface may be a little confusing, and that's why I create these tutorial videos to help step you through what you will be doing as you collect data and answer your quiz questions. Now, you may be familiar with nuclear energy. Here on Earth, the type of nuclear energy that is generated through a process called nuclear fission. Fission means to tear apart. And what you do is you take a big old ungainly type of element, such in this case, this is uranium-235. Notice it's got 92 protons, 143 neutrons for a mass number of 235. So this is an isotope. It's a radioactive isotope of uranium. And you smash that uranium with a neutron. That's what this stands for. And in the process, you produce two daughter elements called krypton and barium. And as a byproduct, you wind up with 3 more neutrons. But essentially what you're doing is you're splitting a big old atom into smaller atoms. And in the process, you liberate energy. That's what nuclear fission is all about. Your book does a nice job of describing nuclear power. In fact, it's got a nice nuclear fission reactor box on page 348, because with nuclear energy, if you're going to use it as a energy source, it just can't be a one-time thing. It's got to be something that keeps on going on, and so you kind of depend upon a chain reaction. And so in the case of this little example here, you got a neutron that collides with the nucleus and winds up creating 3 neutrons, and each of those neutrons can then be used to initiate another reaction. So you get a chain reaction going on, and that's what nuclear fission reactors depend upon. That chain reaction helps to sustain the energy production and allows you to heat water and turn the water into steam. The steam spins turbines and generates electricity. Now, you need to control things, because if things get out of control, then you can have essentially a runaway chain reaction. And so nuclear reactors have boron and other things that help to soak up some of those neutrons that are produced from the chain reactions, so that you can keep enough neutrons to keep fission going along, but you don't want to create too many, in which case you would have a runaway chain reaction. None of us want that. At the heart of nuclear energy is Einstein's equation. Einstein had the unbelievable insight that energy and mass are essentially the same thing, and they are related by this what looks like a very simple equation, and it actually is. What's amazing is that he had the insight to realize this relationship, that energy, which is E stands for energy here, is equal to mass And then the c here stands for the speed of light. Now the speed of light is a large, large number. Again, light is really fast. It's not infinitely fast, but it moves along very, very quickly. So light moves at a rate of 3 times 10 to the 8th meters per second. That's 300 million meters every second, how fast light moves. That is this c value. So think about that huge number, and think about squaring that huge number. That winds up giving you 9 times 10 to the 16th when you square that value. That is such a huge number that even a small amount of mass can turn into a huge amount of energy because of the relative values here. Now, some of the other stuff in here is sort of inside baseball, but what is important for you to understand is that in nuclear energy, a small loss of mass, that's this triangle here stands for delta, it's a change in mass. So a small change in mass can wind up resulting in a fairly large amount of energy. And it's that energy that we're really after in nuclear reactions. Now here on Earth we use mainly nuclear fission, but stars use nuclear fusion to produce energy. But anytime you are producing energy nuclearly, the amount of energy that's produced is dependent upon this Einstein's equation. And one thing that this graph points out is that nuclear mass, that's the mass of the nucleus, increases with atomic number, which makes sense. Because remember, atomic number, as you go up, that means you've got more and more protons. And with more protons, you have more neutrons. And that means overall more and more mass. And that's why you have this shape, where atoms with a small number of protons, such as hydrogen, helium, the mass of the overall nucleus is not going to be that much. But as you get up into heavier elements, uranium, plutonium, et cetera, with much larger atomic numbers, they're going to have a lot of neutrons, and therefore you're going to have a very massive nucleus. What's really interesting is if you take the total number, or if you take the overall nuclear mass, the mass of the nucleus, and divide by the number of nucleons. Remember, nucleons are neutrons and protons. So if you add up the number of neutrons and protons and divide that into the nuclear mass, you wind up with a quantity called mass per nucleon. And it turns out that the mass per nucleon will vary depending upon the element you're dealing with. And it turns out that when you do this math, you wind up with this curve down here, which is really interesting, which shows that hydrogen, way down here at atomic number 1, has a large mass per nucleon. On average, the mass of its proton is larger than the mass of a proton in a helium atom, or a lithium atom, or a boron atom, et cetera, et cetera. So you wind up with this curve here, and this curve is very interesting because what this means is that because of the large mass per nucleon in hydrogen, when you combine hydrogens via nuclear fusion to create helium, you wind up with a little bit of mass to give. So it turns out that when you combine 4 hydrogen protons into a helium nucleus, which is essentially 2 protons and 2 neutrons. So those are your 4 hydrogen protons, and they become a helium nucleus. And the helium nucleus has 2 protons and 2 neutrons. I'll put the neutrons in blue here. This is kind of like a little recipe, But your result, your product, your helium nucleus is less massive than your ingredients. So it appears like there's been some mass lost. Well, that change in mass is the energy that is liberated in the fusion reaction. And it turns out that everything over here, all these elements, which are your lighter elements, your small atomic numbers, when you fuse them, you can liberate energy. Over on this side, these more massive things, notice that it wouldn't make a whole lot of sense to fuse these elements because it would take more energy to make that reaction happen than the energy creates. So these are all fissionable elements. These ones make more sense to tear apart. You take a large thing like uranium and you let it decay, you let it be torn apart, and that liberates energy. Whereas over on this side, these elements are ones that are more it's more useful to fuse them. So these are your candidates for fusion reactions. And the ones over here are candidates for fission reactions. And this is just a closer look at that graph we saw earlier. So remember, everything to the right of iron, these are all fissionable materials. And to the left of iron are fusionable materials. And notice iron's stuck in the middle there. Iron, it doesn't help you to either fuse or divide, fission iron, because it's always going to be a losing battle. It's always, when you're dealing with iron, it's always going to take more energy to make iron react. Now, yes, you can smash two irons together in fusion, but it takes more energy to make that happen than the resulting reaction liberates. Same thing with fission. You can split iron apart if you want, but it's going to take more energy to make that happen than you're going to liberate in the reaction. And that's actually a very interesting result and explains a lot about astronomy. But anyway, this just kind of shows, again, these are fissionable materials, krypton, barium, uranium. These things make more sense to tear apart. To the left of iron, again, these are your fusionable materials because of the mass per nucleon that is demonstrated in this graph. So you might wonder, which is better, nuclear fission, nuclear fusion? Well, nuclear fission is the one that's more commonly done here on Earth. The problem with nuclear fission is that you take radioactive materials such as uranium and you bust them apart and you liberate energy, but you're left with byproducts which themselves are radioactive. So you wind up with a lot of radioactive waste, and part of the problem is what do you do with all the waste? Nuclear fusion, on the other hand, such as what the sun does, it takes hydrogen and creates helium. So the product is helium, which helium is relatively harmless. The problem is that fusion is really difficult to do here on Earth. The sun has no problem doing fusion. Other stars have no problem doing fusion because of the temperatures and the pressures at the core of those stars. On Earth, to create similar conditions, it can be done. You can do nuclear fusion, but you have to contain the reaction with huge magnetic fields. And the amount of energy required to create the field to contain the reaction it takes more energy to create the conditions necessary than the fusion reaction can produce. So at our current state of technology, it's a losing battle. That's not to say that someday scientists will figure it out, but right now, thermonuclear fusion in a controlled way to actually generate electricity is not quite worked out. Now, nuclear fusion is used in the hydrogen bomb, which is more of a destructive use of this technology. As I mentioned before in Chapter 1, or in Module 1, it's always useful to go through the readiness assurance test. Now that we've done all the slides, done all the content of Chapter 16, go to the end of Chapter 16, you're going to find, at the end of the chapter review questions, you're going to find a readiness assurance test, an RAT. And again, the textbook does not provide answers. I encourage you to go through it first before looking at the answers. But if you want to check yourself, here are the answers to the readiness assurance test.